Okay, so welcome back to everyone who is joining us on our natural language processing series. To those of you who are new and this is your first session with us in the series, you're very welcome. Today's session is looking at topic modeling with Azure Machine Learning. It will run over the next 45 minutes to 1 hour. That's inclusive of any Q&A. So any questions you do have throughout the session today, feel free to drop them into that Q&A window. The Q&A is being moderated, so we'll make sure all questions are answered by the end of the session. Also, just keep an eye out for any useful links that we'll be posting into that window as well. Just a reminder also that this session is being recorded and it will be made available to watch on demand on the Microsoft Reactor YouTube channel shortly afterwards. And again, I'll post a link into the window to where you can find that. So just to quickly run through our code of conduct for today before we get started. So this is just a reminder to everyone who's with us today to be aware of others, be friendly and welcoming throughout, and just understanding of differences of opinions if we're seeing anything like that throughout the Q&A today. So today's session is being led by Fatos. We're delighted to have him with us today. Fatos is part of the Cloud Solution Architect team within Microsoft UK, and we'll hear from Fatos just shortly. Just a reminder then of where we are in this series. So today marks episode number 4 in this series. We've already looked at rom-com or not level 2, slaying machine learning with Buffy, and last week was an overview of Azure NLP solutions. Upcoming in this series are the following sessions, which you can see. So they're at the same time every week. And you can register for them through Meetup or the Reactor site as well. So without further ado, I'll hand over to Fatos today to get us started.
Great, thank you, Emma. Okay, so let me share my screen. If there is, yeah. Okay, so Emma, let me know when you can see my screen.
Yeah, I can see that fine now.
Perfect, thank you. Great, so hi everyone. So welcome to this session of the NLP series, Topic Modeling with Azure ML. My name is Fatos Ismali. I'm a Data and AI Solutions Architect at Microsoft. So I work with, I'm part of this organization called the Customer Success Unit at Microsoft. And I work with various different customers around our data and AI solution architecture role, advising them on different AI implementations and ML implementations, working with our data platform, PaaS services within Azure, and yeah, just generally working in this space within Microsoft. Outside of Microsoft, I run a community of data scientists called the Data Science Initiative, which you probably have seen, and you have probably used that to register for this event as well. So I've been running that since 2013, when data science was just about to kind of get hot and become mainstream. So it was a community that I opened to kind of connect with people like you, like-minded individuals in the space, and kind of a facilitated environment for people to connect and share ideas and experiences within data science as well. Perfect. So what I'm going to do this session is I'm going to talk about topic modeling, which is a really hot topic right now, especially with different types of customer, like say experience strategy that many customers from Microsoft and others that I've seen are looking to implement, and it's a really trendy topic right now. It's something that can be used both from an exploratory perspective and also from a unsupervised learning perspective. So I'll talk about this in more detail. I'll show you a few examples. I'll go through the Azure ML technology itself as well, just give you a brief overview of what that is and how that looks like. And then we'll go through a series of examples using Azure ML and some open source packages that can enable you to do this topic modeling in Python. What I'll do right now is I'll turn my camera off just to save some internet packets, because my internet speed is not that great at the moment. So I'll turn that off and I'll proceed. So the way I was thinking of approaching this, instead of diving straight deep into the technicalities of topic modeling, I thought let's actually go into this topic using a use case that I've seen many of our customers wanting to implement with topic modeling. So if I click on this, yeah. So let's start with a use case. And the use case is around call center analytics, right? So every company out there, almost every business out there has a call center function within their business. And usually what they want to do from that call center on top of the operational side of things, which is managing customer requests and queries from their customer base, they also want to provide some or do some analytics on top of that data that comes from that call center function. And the data typically comes usually in the form of speech. So you will have to transcribe that speech into text and then get some intelligence out of that text, some insights out of that text. And you will see an example of how you transcribe audio files in the next session after this one, which will be run by Kayo, one of my colleagues. So today we'll cover what you can do with text once you get that transcription, let's say, from the speech audio files. And if you think about the customer experience within call centers and just generally, there's so many touch points that you as a business need to think about when kind of embedding or going through this journey. There's from the point of client contact all the way to experience monitoring and reporting. There's so many touch points where you can embed AI functionalities and AI capabilities to enhance your offering, to enhance your front office offering, your back office analytics for your internal teams. And that's going to be our main focus for this session, this back office element of the customer experience. And we are going to primarily focus on two elements of this back office function. And that's where topic modeling can be applied, this conversational analysis, real-time insights on geolocation data, routing to the best agents, right? These are elements that can be enabled or can be, let's say, yeah, that's the right word, enabled by a function like topic modeling. And of course, sentiment analysis is another type of insight that you can apply on textual data. Conversational analysis is another one. And then routing to best agents. So once you understand, for example, what that customer request is coming from or what that query is, you can actually take that query and route it to the right agent instead of having the same agent answer all types of queries, which can increase the load on that agent and become a very inefficient process. So that's what topic modeling can enable you. You can identify certain categories of queries, and then based on those categories, you can route those requests, route those queries to the right agent within that call center. And I picked call center because I could have picked any other example where topic modeling can be applied, and there's no such like a shortage of lists of use cases where you can apply topic modeling. But I feel like this is one that is really pertinent, especially in this day and age, I guess, with COVID and all of that. Where lots of businesses are operating online and asking or answering questions from customers completely online. So it's becoming a really trendy topic right now. So what is topic modeling? So probably some of you are completely new to this. If you probably have heard of NLP, natural language processing, and topic modeling is basically a technique or one of the techniques of natural language processing that enables you to extract structured information from unstructured pieces of text. And that text can be anything. It could be a Word document, it could be a PDF document, it could be an article about the news, it could be an article, or it could be a speech transcription like we're doing today. It could be anything that is unstructured in a text format. And usually what happens is you take that unstructured text, you have this algorithm that does the topic modeling process, and then out of that algorithm, you get some themes or topics that you're interested to kind of extract or find. Now, when it comes to actually implementing a topic modeling process, you have to, of course, let's say with the use case that we have at hand currently, the call center with all the transcriptions that we're receiving in the form of text. You probably are seeing stuff like this. So customer requests like I forgot my debit card PIN number, or I need to order 3 packages for today, or I want to cancel my account. These are all, typical customer queries that can come. And if you were to do this using a different type of approach, let's say if you wanted to build an algorithm that tries to identify which or category these calls belong to, you could pick it. You could take two approaches. You could take a classification approach where you have to manually label each of these calls, or you could take a topic modeling approach, which does this automatically for you. If you were to manually label this yourself, this will be extremely time consuming, especially if you have hundreds of thousands of calls, like I've seen with some of our customers. That will be extremely time consuming, and it will make your life miserable as a machine learning or data scientist. Even Grumpy Cat hates that, right? So he used to love machine learning until he started manually labeling data. So topic modeling to the rescue, and this is our topic modeler. He's saying hi. So he's interested to kind of pick all your unstructured pieces of text and automatically classify them into certain topics. And notice here a difference from the previous slide, where you saw topics in red, blue, and green, and purple actually had names attached to them. In this case, the topic modeler does not know what is classifying it. It just knows that this is a distinct category or distinct topic from all the other ones that it's seeing. So it's finding that calling with regards to order cancellation, I want to cancel my last order, is a specific topic on its own. And then I forgot my debit card PIN number. It's also a specific topic on its own. I need to order 3 packages for today. That's another topic on its own. So it's finding these, let's say, arbitrary topics. It classifies them into categories. It calls them randomly, like topic 1, topic 2, topic 3. And then it categorizes all the relevant calls, in this case, under that topic. So that's what the topic modeler does. And then it is up to the human to actually go and interpret these arbitrary topics, like topic 1, what does that indicate? What does that entail? Topic 2, what does that do? And then, hopefully that will put a smile on your face, not on the Grumpy Cat, obviously. He doesn't like to smile at all. So that's what the topic modeler will do, right? So we'll get the topics that you see here. You see each topic is basically or each document. Rather, in this case, a document would be a call transcription from the call center analytics. That document or that transcription will contain multiple topics potentially, right? It doesn't have to be just one topic. And within each topic, you will have multiple terms. So the topics will contain a lot of terms. And you can see here, topic 1 has these terms like order, cancellation, cancel, call, etc. Topic 2 has forgot, PIN, number, card, issue, etc. So they are like categorized or distinguished based on these terms that tend to appear very frequently when we're talking about, let's say, topic 2 or topic 1. And then it is up to the human to take those categories, these arbitrary categories like topic 1 to topic 4 and their corresponding terms, and actually do that human bit, which is that interpreting bit. So the human will say, okay, I found topic 1 to be about order cancellations based on these terms that I'm seeing. And I found topic 2 to be about forgot, PIN, number, card issue, to be about card PIN issue. And then a human will basically manually name those topics. And then, of course, because the algorithm has done all that hard work in the background to classify, not just to find the terms that belong to each topic, but also classify all the calls that fall under that topic, you now have the interpreted topics from the human with all the corresponding calls that belong to those specific categories or topics. So order cancellation has 256 calls, card PIN issue has over 1,000 calls, and so on. So as I mentioned, topic modeling is different from topic classification in that topic modeling is a unsupervised learning approach, right? So there's no labeling required to extract topics from a piece of unstructured text, whereas topic classification relies on manually labeling or getting some labeled data and then training an algorithm based on that labeled data. So topic modeling is also referred to as an exploration technology, or something that you use to discover unknown unknowns, if you will, in your data set. Maybe you're starting from scratch, maybe you don't have a question to answer, you just want to explore what your data contains, what your unstructured data contains, so you can use this topic modeling technique to uncover all these different insights about your data set. And as I mentioned, in topic modeling, the input will be lots of different pieces of unstructured text, which could be anything. In this case, will be called transcriptions. Outside of those pieces of text, you will have these arbitrary topics that are named topic 1 to topic n. Each topic, arbitrary topic, will have a number of words underneath it that define that topic. So now let's explore a few topic modeling algorithms and go a little bit deeper into them. We're not going to go too much into the theory and the maths behind it, because we want to make the session as practical as possible. So we'll show you a few demos of how to actually deploy a topic model into production using Azure ML, and then also how to use open source algorithm, how to actually develop these in using the open source packages that you see out there. So for topic modeling, we're going to consider these three algorithms to start with. So LSA, Latent Semantic Analysis, PLSA, Probabilistic Latent Semantic Analysis, and Latent Dirichlet Allocation, LDA, which is usually the go-to algorithm for topic modeling, the LDA one. So we'll cover the LSA just to kind of give you some background and some differences between them. So in all of them, usually LSA, PLSA, and LDA, you start with a document term matrix. So the document term matrix is basically a matrix of rows and columns, where rows are the documents. In this case, they will be they're not actually showed here. The way I'm explaining it is the reverse of how it's shown here, but essentially it's the document term matrix or term document matrix, whichever makes sense for you. But you get a piece of text. In this case, we'll get a transcription of a call, and we'll take that piece of text, we'll treat that as a document on its own, and then all the terms within that document will be the terms in this matrix. So you will have loads of rows indicating the individual documents, and then loads of columns indicating all the terms in all the rows. So it will be a very sparse matrix. There will be loads of empty cells because some words will not appear in other documents, and some words will appear. So it will be a really big matrix of words. And when you're dealing with such a big matrix of, let's say, loads of documents and loads of terms, you have to reduce the dimensionality, and this is what LSA does. So one of the steps of LSA is to pick up this document term matrix and reduce it to something that is more manageable for a machine learning algorithm. So one of the techniques that we use to reduce the dimensionality of a big matrix like this is called SVD, or short for singular value decomposition. And what that does is it takes a matrix like this, term document matrix or document term matrix, whichever you want to use, and it basically constructs these three decomposable matrices that you can take and actually do some interesting stuff with it. And that's what latent semantic analysis does as part of the process. It basically leverages this SVD function to create these matrices, which contain the topics. So this U matrix here that you see, the columns of that U matrix are the topics corresponding to the terms, and then the V matrix here, where the columns will be actually the topics, not the documents here as it's highlighted. There will be the topics, and then the rows will be the documents. So you will have this two matrices of topics and terms and topics and documents, which then you can take and do some similarity matching between them using the cosine similarity function that you see here. That's the formula, but there is a easy to use Python function that I'll show you later, how you can actually take that and build it into a Python function. But the cosine similarity is a distance function that allows you to kind of check the similarity in a Euclidean space of two different, let's say, vectors to see how similar they are to each other. And vectors here being, for example, a document with all the terms, or a document with all the topics, and a term with all the topics. So you can do that kind of analysis with similarity check. So that's what LSA is doing in the background. And then you have another version of LSA, which we call probabilistic latent semantic analysis. And again, this is using a document term matrix, but instead of using the SVD function for decomposing the massive document term matrix into these U and V smaller matrices, it's actually using a probabilistic function, which basically models this topic assignment and document-specific topic distribution, which gives you this formula where you are essentially, given a document D, topic Z is present in that document with probability P of Z giving D. Given a topic Z, word W is drawn from Z with probability P given, P of W given Z. And then to estimate the, what it's trying to do is just trying to take that probability function, is trying to essentially generate what it sees in the document term matrix, the input document term matrix, using this probability function. And the way it arrives at that generation of those document term matrix that it sees in the input is using this estimation function called maximum likelihood estimation to arrive at that. So this is just a probabilistic version of the LSA that you saw earlier. Again, both LSA and PLSA are not heavily used in the industry. LDA is usually the one that is used the most. And that is basically, again, it's a variation of PLSA. So instead of using a probabilistic function, this is actually now using a Bayesian variation of PLSA, right? So now you have this concept of the Dirichlet distribution. That's where the Dirichlet name comes from, which is basically a probability distribution on top of a probability distribution. Hence why you see this graphical representation, which is this almost like a box within a box, or a distribution within a distribution. So that's what LDA is doing. Is basically is giving you this document topic distribution over the word topic distribution, and it's trying to model that using this probability function that it has. And again, as you can see here, if you take a piece of document, as I mentioned earlier, that piece of document, which in our case will be a call transcription, will contain multiple topics indicated here by the colors red, yellow, and green. And within each of those topics, you will have different words that represent those topics. And then in this topic proportions graph that you see here, the distribution, you basically have, what is the contribution for that document, of that topic for that document, right? So for example, there's 33% contribution of topic red in this document, there's this 8% contribution of topic yellow in this document, and 7%, and so on. And usually this number adds up to 1 at the end of it. So this is probably not a great representation of how it would look like in the real world, but that's how it does it at the end of it. So topic modeling using LDA in Azure ML is something that we have baked LDA in as part of Azure ML user interface. So you don't have to actually develop this from scratch in terms of like building the Python code to do it. Of course, you have to do some potentially some Python code if you want to, let's say, pre-process the data, just like we're going to do now when I'll go through the demo. But essentially, there's 3 main phases to this whole process when you actually implement LDA in Azure ML. You first have to get the call center transcriptions, which are stored in a blob storage account. A blob storage account is a service within Azure. So Azure is a cloud service and is a cloud, and blob storage accounts are just one of the services that we have. And it's used basically for dumping data in there. So you can dump CSV data, you can upload PDFs, Word documents, SQL tables, whatever, right? So all kinds of unstructured and structured data sets. And in this case, we're going to store JSON files into a blob storage account, and we're going to have Azure ML read those JSON files and then apply LDA on top of those JSON files. And I'll show you how we process those JSON files to get the piece of text that we need, because of course JSON files have all types of nested structures within them. And then what happens next in the topic modeling experiment within Azure ML is that we import those call transcriptions in that Azure ML experiment. We pre-process them, so we take the pieces of text that we're interested in those JSON files, and then we take that piece of text, we clean it, we remove punctuation, we remove stop words. And then we apply the topic modeling algorithms, which can be LDA, and that's what I'm going to show you today, or it can be anything outside of LDA or outside of Azure ML. So you can actually integrate your own open source implementation of a topic modeling algorithm. Once you then run that, there will be 2 data sets that we're going to output, and I'll show you how they look like. One of them is a CSV file that contains the topics. So we decide how many topics we want during this process. We can take, for example, 20 topics or 15 topics. It depends on how much we want. Of course, you can evaluate that. So you as a data scientist will need to go through that potentially in different types of iterations until you figure out, what is the optimal number of topics that you want to use based on what the terms under each topic are. And then the other CSV file that we're going to output is this topics per transcription. So we're going to actually get the topics for each transcription call and actually show the terms in each of those and the probabilities of those terms for that specific transcription. Okay, so we get into that one. So let's let me go back to my browser screen now. So okay, so now what you're seeing here is the Microsoft Azure Machine Learning Service. And this is the user interface of Azure Machine Learning Service. It has this concept of notebooks where you can basically provision virtual machines and have multiple people collaborate with notebooks, for example, like I'm doing here. Each person, for example, can have their own folder where they do their own changes, and people can share notebooks with each other. You can run Jupyter interfaces on top of this, like the standard Jupyter interface, etc. So this is where you can do your exploratory analysis. Then this tab here is the Automated ML tab, which allows you to kind of democratizes machine learning to a larger audience, so people that are not particularly, let's say, savvy in terms of the programming languages aspect. So if you want to maybe build a algorithm like a classification or a forecasting or a regression algorithm, you can actually use Automated ML to create that algorithm for you. So Automated ML will go through a process of selecting the most optimal algorithm for you based on your data set and based on your metric that you have decided to use. And it will do that in parallel. It will try multiple algorithms until it finds the one that performs the best in terms of the metric that you've chosen, which could be accuracy, recall, precision, weighted accuracy, etc. And then you have this designer, which is another way of interacting or building Azure Machine Learning Services experiments. And this one is a more for a graphical user interface, like a drag and drop type functionality. So there are some templates here that you can actually just click on and see how you can build. And examples, for example, this one is building an image classification using DenseNet, and it kind of shows you how to import an animal images data set, how to pre-process that, how to split image directories into training and testing set, how to apply a PyTorch model, and then how to evaluate the model and of course export it afterwards and productionize it. So what we're going to do is I'm going to show you how to use this user interface to build a LDA model. So I've built one already. And what this is showing you is basically showing you a series of steps that don't be overwhelmed by potentially large, lots of boxes here. When we go through this, you're going to find it's actually pretty straightforward. But just before we go into that, on the left side here, you can see that you have all these different tabs. And under data sets, for instance, this is all where I keep all my data sets that I can drag into this view. And those data sets can be CSV files, JSON files, text files, etc. You can also leverage something called sample data sets, which come with Azure ML if you want to just upskill yourself within Azure ML. Custom models, feature selection, functions, statistical functions, machine learning algorithms. All of these can be dragged and dropped here, and you can actually use them without any programming at this point. So you have all the different classification, clustering, regression. There's also some text classification or text algorithms. I think there are text analytics here. So you can actually build Word embeddings from your pieces of text. You can extract n-gram features from text, feature hashing. And this is where that latent Dirichlet allocation is. So you can see this is just a module that you can just drag and drop and put it here. And then you can parameterize that based on some of these parameters that we'll go through in a short while. So what I'm doing here is basically I've stored all my JSON documents in my storage account. And this is my storage account where I have all my JSON documents. So I've categorized them into these so-called, I call them teams, different teams. So you can think of this as maybe, if you're an organization, you can have maybe your departments indicated by a folder name. And within each department, of course, every department, let's say, has an agent that works in the call center function of your business. and that agent is dealing with different call transcriptions. And those call transcriptions have been transcribed and have been stored in this directory for that specific department, and you can see them here listed as JSON files. If I pick just one of these JSON files and I show you the structure and the content of that, this is how it looks like. So this is basically coming from our speech recognition technology, which you will hear in more detail in the next session with Kayo. But essentially, what we're interested in is this display variable here, which contains the entire call transcript. The combined results basically is all the different utterances that are being spoken by, let's say, the agent and the customer. And this display usually has the entire call transcript embedded into it. So that's what we want to get. So we need to traverse this flow of JSON, of the JSON document, and we need to pick up this display variable and pick this piece of text and work with that to do our topic modeling. So that's all these JSON files are basically contain similar type of transcriptions, and you can see here I have loads of different teams. Each of them has their own transcriptions. And what I've done is I've gone into datasets. So I'll open a new one here. This datasets has all my registered datasets. I can create one here. I can go from data store, from local files, from web files. So usually I go from data store because data store means that you're connecting to your blob storage account. And let's say I give it a name, test DSI. You can select what is that file. In this case, I'm going to have it as tabular format. I click on next. And in here, I've already defined my data store, but basically this data store here indicates the reference to the container. So this DSI JSON folders is basically a data store, represented as a data store here. So I click on that one, select it. If I browse that, you can see I see all those folders that I showed you in my storage account. So I click all of them. So I want to get all the files and the subfolders or subfiles, files in those folders. Then I click on next. And in the next screen, I will be able to see, the files in those folders, the JSON files. And this usually takes like about a minute or two to load this dataset preview, especially if you have, a long list of files. But there you go. So you have an ID of each of the individual files of all the files in all those folders, and you have the line, the JSON line, as you can see those audio file results, audio file name, which basically you saw here, audio file results. Audio file name. So the entire JSON structure is loaded here. And then I go next, and I create a data set. So I'm not going to do that because I've already done that. And just leave here. So that's my DSI JSON folders, which is this bit here. So if I go back to the previous screen, so all I can do then is I go back to data sets, and I drag the DSI JSON files. I drag it into here, which I've done already. And then I can do something with that data. So I can actually execute custom Python scripts if I wanted to. So I can, let's say I want to pre-process that data. I don't want to run LDA because I need to clean it, I need to pre-process it. So I can embed Python, just normal Python, pure Python functions and scripts within this execute Python script module. And here I'm going through that JSON structure. I'm going to the display, as you can see. I'm picking up the display, and then I'm doing some, the path is basically the path to the file, which is basically the folder name here. So what I'm doing I'm just removing these _1s or _2s sometimes. So I'm just removing the number after that, and then I'm cleaning the path. So that's why I'm calling it path clean. So all I'm doing there is just that. Basically, I'm cleaning the path name, and then I'm doing joining this data set with this DSI team list formatted. And I'll show you why I'm doing this when we talk about Word Embeddings. But basically, just to show you that DSI team list formatted. Sure, if I can open that here. I don't have it here. I can always just go back to here, DSI team list formatted, and explore the data from Azure ML as well. And that will basically just contain these. So I have a team, which basically has these premium accounts, customer support, scheduling, sales. I have sub-teams for each of those teams, like customer experience team, Apple orders, just name some of these as very arbitrarily, Apple customer service, etc. And then associated folder, which is basically that folder structure that you saw in the storage account. And then when I transcribe this, the idea is that I can actually visualize this really interestingly by saying, okay, what topics are my customers talking about in each of these individual teams and sub-teams? And that becomes extremely powerful, because then you can take that insight and that information, and then you can route those requests automatically to the relevant sub-teams as they come in real time. And that's the idea of this exercise. So now if I go back to the previous screen, the designer. So here I'm joining the data. So I'm joining my my JSON files with that DSA formatted, which you just saw. I'm pre-processing it. Again, Azure ML has a pre-processing module which you can use to remove stop words if you wanted to use lemmatization, detect sentences, etc. Normalize stuff into lowercase, all the words. And here, import data module, I'm dragging it because I want to actually include the ability for the customer to define their own stop words, not just the one that you can download from the different Python packages, but you can actually, so this is my stop words, and I can actually put here any word that I want. I can grow this list as I want. Like if I want to, avoid seeing a word in my call transcriptions, I can put that here, and this flow will automatically pick that up, and it will be part of this flow, and you can see that word being removed from the transcriptions. Again, I have another execute Python script where I'm doing some Python pre-processing. Here I'm removing punctuation, numbers, stop words, etc. And then I'm calling the latent Dirichlet allocation on that pre-processed display, which is that piece of text that we have pre-processed. And here I'm saying I want 25 topics to come out of this LDA process. I'm using 2 n-grams, so this is the window of n-grams being terms that I want to look at any one point of time. If I want to normalize them or not, the row parameter, all of these are actually explained in more detail. We don't have the time to do that here at our link in our documentation here, which I'll send it to you. And then I'm selecting the columns here. I'm selecting all the different topics that I want as the output. So 25 topics here. I also want the output CSV to contain the preprocessed display text itself, the audio length in seconds from the transcription file, the team, the subteams, etc. All of that information. And then I'm going to output them into two files. One of them, as I mentioned, contains the results, which looks like this. Right, so now you have the path to the folder in storage count, you have the audio length, you have the team or the path, the folder name basically, you have the team, you have the subteam, you have the preprocessed text here, and then you have the topics, as you can see. So these are the topics and the distribution of those topics for that specific transcription. As you can see here, this one, for instance, this row for this transcription, topic 14 has the highest probability distribution, or the highest probability score, which means that this transcription may be identified by topic 14, sorry. And topic 14 has a confidence of 57 being that topic. And then you can say, for example, for that topic, which is indicated by this best topics. So this best topics is basically picking up the terms of the topic that has the highest probability score. So then I can just see what are those values for topic 14, and these are the values for topic 14. And I can then identify what this is. So me as a human, I can go and interpret these topics, individual topics, saying, okay, this is about, this is maybe about something that happens in Australia, let's just say. So that's how you would do it. So that's what that results file is. And then we also export another file called top terms. And top terms basically just looks like this. So it includes all the terms of the individual topics that you just saw. You can see, for example, this is where the business then can go and say, okay, I understand that these words are actually talking about something, right? It's maybe about account and invoice. So I can name this invoice. And then I go, okay, this topic is talking about, something else. And then I name that something else, and so on and so forth. So that's what the business would have to do to actually interpret those topics and name them to the corresponding business term. So that's what this does. And then once you're happy with this pipeline, you can then actually publish it. So you can publish it so that you can call it as a REST API endpoint, right? So that's what Azure ML gives you. It gives you this really powerful capability to completely productionize this whole pipeline. So once I hit publish, I'm not going to do it because I already did it. I can go into under endpoints here. And here I have real-time endpoints and pipeline endpoints. For example, I have this diabetes voting ensemble, which is a real-time endpoint, which I can test. I can give it some values for all the features that it expects. I can test it, and I can get some real-time results. So I can call this also from a REST API call using an HTTP request, or I can call that pipeline endpoint, which is the one that we're working with, which is that DSI NLP topic modeling pipeline. And this one can be, of course, submitted from this user interface, or it can be called from this REST endpoint that you see here. So you can call this from anywhere, from Python code, from other orchestrating tools out there like Data Factory or Glue or whatever you're using, and actually consume the results of that afterwards, which are stored again in the storage account. In my case, they are stored in this NLP dat container under results of CSV and top terms of CSV. Right. And what you can then do is you can actually visualize this completely into Power BI. So if I open, oh, I don't have the, okay. Let's see if I have the Power BI opened here. Yeah, let's try this one. So you can then link Power BI to those two files in your Azure storage account, and every time you update those files, your Power BI dashboard will be updated as well. So you can show the latest results of your topic modeling analysis, and then you can show those results and share those results with your business stakeholders, so they can see, you know, what is happening with your call centers, with all the different departments, you know, and what is hot out there, what are the usual customer queries that are coming most often. So just to show you that one quickly. Let's wait for this to load a little bit. Okay. Yeah, so you can see like different teams, and then for each team, you can see, for example, you know, what is the percentage of calls that are coming for that team, etc., etc. So you can visualize all of this within Power BI. And then just to go back to the slides, so that was topic modeling using LDA, right? Which is one of the techniques that allows you to approach topic modeling as an NLP technique. Another one is I'm not sure if this is going away. Let's try this again. Okay, hopefully. Okay, maybe that will go away now. Yeah. So another way you can approach topic modeling, and I put it in quotes because it's not strictly topic modeling, but it's a way to actually go around it, is using a word embedding approach. And the word embedding approach is essentially approaching it this way. So you first define the topics and descriptions for each of those topics that you want, right? So here, for example, this is a screenshot of how I've defined them. So I have this Apple sales adjustments, then I have defined some related words that describe that topic. Like these ones, refund, other, write-off, etc. I have another one called Apple sales inquiries that is defined by these terms: balances, credit limit, etc. And then you say, okay, generate the word embeddings for each of the words in the description of that topic, and calculate either the sum or the average word embedding for the entire description. So now I have, let's say, if I'm using 100 dimensions for that embedding vector, I have a 100 dimension array that represents that topic, which basically is the embedding of that description for that topic. And then I say, okay, generate the word embeddings for each word in the call transcription, and calculate again the sum or the average of the entire call transcription embeddings to get that 100 dimensional vector. And then I run a similarity function like a cosine similarity to check how close are those two vectors to each other. And then I say, okay, then go into a loop, pick up one transcription, go through all the topics that I have available. Let's say I have 30 topics that I have defined by the business with all the associated descriptions. Go through each topic and then rank basically for that call transcription, rank which topic is most relevant to that call transcription. And then I say, okay, I found this topic to be the most relevant to this call transcription. And that's how I then arrive at that topic for that transcription. So that's what this approach using word embeddings can do. And usually I've kind of considered only two here, Globe and FastText. which are two implementations of word embeddings. Glove is a very popular one, and it uses these two approaches: skip-gram model and CBOW model. Skip-gram basically looks at the context word given a word, so it looks at modeling the probability of a context word, like the context word here being the mighty Lancelot fought bravely, and the word being knight. And then CBOW is model probability of a given word given a context. So model the probability of knight given mighty Lancelot fought bravely. And this is good because it gives you that way of generating those word embeddings for each of the words, let's say in your description or in your call transcription, and then comparing those word vectors, whether you're using the 100-dimensional word vector or the 300-dimensional word vector that Glove provides to kind of associate the transcription to a specific topic. Another one that is used heavily out there is fast text from Facebook. So they developed this in C++, and it supports 157 languages last time I checked. And unlike working at the word level, this one actually works at the character level. So it does character-based embeddings. And this is good because if you're dealing with call transcription especially, usually people say words that are not grammatically correct, let's say, or maybe you're dealing with a piece of text that is not grammatically correct, written in a grammatically correct fashion. So this fast text embeddings will actually be able to pick that up. Like if you spell the word account, by mistake, maybe you miss the T, for example, account. Word embeddings will say, oh, I don't recognize this word account. But character-based embeddings will actually be able to recognize the word account even though it's missing the T. So that's why this is more, I guess, more robust to grammatical mistakes that humans make. What I'll do is I'll leave you with these two reading materials, which you can read. And this is an approach of combining embeddings, so word embeddings, the concept of word embeddings, with LDA that we discussed about. And this is basically using the word vector that you get from the word embeddings approach, and the document vector, which you get from the LDA, and using both of those to predict the context vector for a given word, like airline here. And this is an approach that people are using, and this person called Chris Moody has written an extensive blog post about this, which I've taken a screenshot from his website. So I definitely recommend you to read that. Another approach people have seen are using is using BERT to do topic modeling. And again, with BERT, what they do is they generate the embeddings using BERT, not like Glove or fast text. So they use a sentence transformer library that allows you to do that sentence and to generate those sentence embeddings. And then they use this UMAP and HDB scan to first do the dimensionality reduction of those embeddings, and then to cluster those documents into a lower dimensional space using HDB scan. Once you cluster those documents into a lower dimensional space, you treat each cluster of those documents as a single document, and that's why I mean by a variation of TF-IDF, because this person, Martin Grutendorf, I'm not sure if I'm pronouncing it correctly, has built a variation of the standard TF-IDF. He calls it the C TF-IDF, which basically treats the whole cluster of documents as a single document, and gives him the ability to kind of rank the words that appear in that document. And then you can say, okay, give me the top 25 words that are the most relevant to this cluster of documents, and then he treats those 25 words as the identifying terms for that specific topic or for that specific cluster. This is a really interesting approach. Definitely recommend you to check the Towards Data Science blog post on that. And then finally, if you're not keen to use Azure ML, for example, to do LDA, you can always take it, using your own Python code and maybe embedding that into something like an Azure Functions. And we have this really good GitHub project called Versatility, which it does not necessarily implement topic modeling, but it provides you an NLP toolkit architecture, and you can actually deploy this within your own Azure subscription if you have one. If you don't have one, you can always sign up for the $150 trial. And you can actually deploy this architecture as you see here, and that shows you how to use popular open source NLP libraries like Transformers from Hugging Face, some of the other ones like Spacey, and use those to actually deploy them into production using these serverless-based architecture that you see here, not Azure ML. So Azure ML is not being used here, even though it's being shown here as modeling under AML here, but it's not being used at the moment. So everything here is implemented using Azure Functions and App Services. So you can actually implement LDA as an Azure Functions or Word Embeddings as an Azure Functions, and so on and so forth. And you can use this template to do that. Also, if you really love all this stuff about NLP and you want to practice practice more in this space, and maybe Lida has covered this already, but there's this GitHub repo called NLP recipes from Microsoft, which allows you to go through different types of scenarios like text classification, named entity recognition, text summarization, question answering, which you saw that versatility basically implements that pattern called question answering. You can go and actually use some of the state-of-the-art algorithms out there to actually get hands-on practice with some of these. And there's loads of Jupyter notebooks available at this link for you to try out using open source technologies, of course, in all of those. Cool. So it's 6:51, and I think, or sorry, 5:51. I'm in a different time zone at the moment, so I'm happy to stop here and take any questions from the audience at this point.
Yep. So thank you for that. We do have a few questions. So we'll start in reverse order. In your experience, which of the approaches, LDA topic modeling, LDA to VEC, and BERT topic has delivered the best results, and why?
Okay, LDA to VEC and LDA. So LDA is probably the one that you should start with to begin with. It gives you some good. It gives you a good approach to arrive at some arbitrary topics and then with the associated terms. However, it does not take into account the, let's say, for example, what Word Embeddings gives you, which is the contextual understanding of a sentence, for instance, which, as I showed you with Word Embeddings, you can actually, using the SIBA or the skipgram model, you can actually get the contextual awareness of each word that appears in your documents, or in this case, transcriptions, and embed that, or get that embedding from those Word documents and combine that with the LDA document embeddings. And of course, the embedding approach, the combined approach usually tends to work better. So what I've actually found is just using that approach that I mentioned earlier, the word embedding approach, just using, for example, fast text, where you actually define those topics beforehand, and then you use fast text to find similarities between your transcriptions and the descriptions of your topics. That tends to work quite well and actually much better than what LDA gives you. So in my experience, using the word embedding approach to find similarities between your data points, your documents, and the descriptions of your topics that you have defined is a much better way to get to basically implement topic modeling in my experience. So I've used Globe and fast text. Fast text seems to work better, so I would definitely recommend you give that a go.
Okay. So next question. I think the LDA algorithm complexity will be proportionate to the number of topics. Does that also imply the Azure Machine Learning compute resources usage will be proportionate to the number of topics, hence also the compute monetary costs?
Okay, good question. In terms of compute power, so I haven't actually done like stress testing in terms of how much Azure ML can handle, but I haven't seen a scenario where we've run out of compute, but there probably may be. So there's no fancy optimization that are happening in the background from Azure ML in terms of LDA itself. So actually, Azure ML is using the scikit-learn implementation of LDA, so it's not doing any optimizations on top of that. So whatever runs in a VM, it will actually, it will run. If it doesn't handle that, then you will just need to scale up the compute power of your, let's say, training cluster within Azure ML. So it depends on the Azure ML training cluster size, I guess, to cope with that. But I haven't gone so far to say, okay, I'm hitting a performance issue because my model has become too huge now. But it's a good point that I'll check if others from our colleagues have encountered that.
Okay, thank you. Next question. How do you decide if it is better to prioritize most frequent words or most discriminative words for your topics? Most
frequent words versus most discriminative words. I I guess so. I think the problem with that. So, for example, with PLSA, that used to be a problem. Because, for example, if you have a document in PLSA that the model hasn't seen, for example, you've gone through a single iteration of PLSA and you've gone through all your documents in the corpus, and you run it again for a new document, and if that document hasn't been seen in the first iteration, it will not be picked up later by a PLSA. That's one of the drawbacks of PLSA. LDA seems to handle that pretty well, so you can generalize on new topics as well, and new documents. Sorry. In terms of the frequency versus discriminative, I guess it depends on how you implement TF-IDF. If you're using TF-IDF, you should be able to. That should be able to handle that. To be honest, it shouldn't be a problem. But yeah, more than that, I don't know what else to add to that.
So it's also a question on, is there a GitHub repo for the example that you can share?
Not at the moment. So what I'm planning to do is basically hosting all the codes. And by the way, I didn't have enough time. That's why I didn't go through the notebooks. But I have added like a series of notebooks here that just go through the Word Embeddings approach and how you can use that to generate the similarity functions and all that. So what I'll do is I'll upload this into a GitHub repo, and then also share the designer view here, which I can share now as a Python notebook as well, which is a new feature that came with Azure ML. So all this designer view here that you see here, I can share it as a Python notebook, and also share a few screenshots of this if you wanted to, let's say, implement this or kind of replicate this flow as well. So I'll share that later. Maybe not today, but tomorrow in a GitHub repo, and share that with you.
And another question's come in. Can we fine-tune Transformer and BERT on Azure AutoML?
Good question. So in AutoML, you can use the BERT featureizer to, let's say, extract BERT features from your pieces of text. I don't think you can fine-tune it. I think it's using the the base BERT pre-trained model. I don't think you can fine-tune it as far as I'm aware, but I may be wrong, so I need to check with the product team. But as far as I'm aware, at the moment, you just use the pre-trained model, which is I think it's the base undistilled version of BERT and unpaced version of BERT. Sorry. And then you use that to just extract the features using the BERT featureizer, and then go through the next step, which is the classification bit. But I don't think you can fine-tune it within AutoML itself.
Okay. So another question: how can you source control pipelines built in the designer?
Good question. I don't think. I mean, Robin, you can also chime in here, but I don't think you're able to do that at this point. As far as I'm aware, I think that the designer here that you see, for example, I can actually export this to code like Python notebook, and then use that as use your own version control software to version control the output or the export of the notebook, the exported notebook here. But there's no inbuilt feature within the designer interface that links to a GitHub, let's say, repo or an Azure repos within DevOps to allow you to version control this view. So there's no straight answer to that, I'm afraid, at the moment. Probably a feature that the PG is actually working on at the moment, but it's not there yet.
Yeah, I don't know any way apart from you could possibly get the underlying files from the blob storage that comes with the Azure Machine Learning Studio, but that's almost certainly unsupported in doing that, and probably not very easy to do either.
Yeah.
Okay, so we're at time. So just a big thank you to Fatos for giving this talk. And Emma, any kind of final words from you?
No, I think you covered just about everything. Thank you everyone for attending today, for all of your questions. And if you do have questions after today's session, you can always reach out directly on the Meetup page where you most likely signed up for today. So feel free to do that. If not, I hope to see everyone back again next week at the same time for our next session. Fatos, thank you so much again for delivering today's session, and look forward to welcoming you back again soon.
Great, thank you everyone. Thank you for joining today.